The last unit, Unit 4, is going to deal exclusively with the antiderivative or taking the integral of a function. We've spent last couple units talking about how to take the derivative. Now we're going to be doing the reverse procedure for all of those derivatives. Now you're still going to need to know how you took those derivatives when trying to calculate what the actual antiderivative is. So let's take a look up here. All right. A function f is an antiderivative of the function, capital F is an antiderivative of the function little f if we have this f prime of x equals our f of x. So we're going to be using the capital letter F to illustrate that something is an integral of some other function, or an antiderivative of some other function. The prime works as it would with the derivative. So what that's saying, what I've highlighted there, is if I take the derivative of some function, capital F, it's going to equal another function with a small f. And again, that's for all x in our domain, or whatever the domain of f is. It changes depending upon what our function is. Like a natural log function goes from 0 to infinity without including 0. All right, so we have another theorem. This one states let f be an antiderivative of little f, so capital F, little f, over an interval I. Then there's two things. One, for each constant c, the function f of x plus c is also an antiderivative of little f over I. So what that basically, let me read the second one. If g is an antiderivative of f over I, then there's a constant c for which g of x equals f of x plus c over I. Basically what this does, let me give you a little example as to what this is and why this is. So say we have some function 2x, all right? So let's just say, we'll look for the derivative of 2x. So this is other notation. This part here means the derivative with respect to x. All right, so we're going to take the derivative of 2x. Well, that's simply just 2, right? We bring the 1 down, multiply it by the 2, subtract 1 from 1 to get 0, and we get 2. This is something that you've been doing for quite some time. Shouldn't be an issue. All right, but say now, given this, my function equals 2. I want to find the f of x for this. So I want to find the antiderivative. Well, certainly 2x works. We've just taken the derivative. So f of x could equal 2x. All right, there's no problem with that. Could it also equal 2x plus 7? Well, let's find out. If we said f of x equals 2x plus 7, f prime of x equals 2. That also works, right? So this one. Well, what about f of x minus 4? Capital F of x. Sorry, capital F of x equals 2x minus 4. Well, that derivative is also just 2. So what this c is, this constant, it doesn't matter what we put down there as long as it's a constant. It's going to give us the same antiderivative, taking the derivative of a function with any constant will give us the same value. So it doesn't matter what I have in for that c. There's an infinite number of different capital F of x's that will satisfy the antiderivative of the function 2. Okay, so All right. So this is other notation that we're going to use. This symbol here. That means you're going to take the integral. That means the integral of, or it's integrand. The indefinite integral means we don't know what values we're going to and from. We're basically taking on the entire domain. So there's another, when we get to the definite integral, there'll be a value, some number up here and below. Well, that was the best color. Let's try this. There'll be a number above and below that little slash, the integral symbol. Okay? We'll get to that later on. All right, but that's the notation we're going to use. So this simply means the integral with, this is the integral of f of x and the dx means it's with respect to x. If it was something like dy, we would be integrating y, and that would kind of mess us up a bit. It'd actually be a little easier to do, but it doesn't matter. All right, so normally how we're gonna write this, and something I'll need to see on quizzes and tests, is this plus c. If you're doing an indefinite integral, that plus c is that constant that you can add to any different capital F function that will get you the same derivative. Because again, the derivative of any constant c is 0, and we're doing the reverse procedure. All right, so there's the very first way we learned how to take the integral, the derivative, was the power rule. So for derivatives, we had y equals ax to the n. We had y prime equal a times n x to the n minus 1 for each of the ones that we had. Well, this is the reverse procedure. So what's happening is, so instead of multiplying by the value that we had and then subtracting 1, we're then dividing, we're adding 1 to the exponent, and then we're dividing by 1 plus that, which will give us the reverse procedure, the inverse procedure, and you can solve for that if you'd like. So a couple of examples. These are from your book, from 4.10. 497. If we have the function f here, we want to find the antiderivative. Let's use the notation. So our capital F of x will equal the integral of this 5x to the 4th plus 4x to the 5th dx. Now, we can break this up into two things in the same way that the sum of the derivatives was equal to the derivative of the sums. The sum of the integrals will be equal to the integral of the sums. So really this equals these two guys here. You don't need to use this notation. You can just perform the integral as you would have performed the derivative, only using the reverse procedure. So here we have it equal to, let me scroll down a little bit. All right, so using our formula there, our exponent is 4, so we're going to add 1 to that. So this is going to be 5x to the 4 plus 1, and it's all going to go over that same 4 plus 1. All right, that's that. And then we add a c. And we'll label it C1 for now. It doesn't matter. It's just a number. And this next one, all right, that's a 5. So we have 4 times x to the 5 plus 1 over 5 plus 1. And this is going to add some other c. Okay. So we can clean this up. It's not hard. These become 5. So 5 over 5 is just 1. So this is just x to the 5th. Plus c1, but I'll get to that. And then this one is plus 4 over 6, x to the 6th. Let me just leave it like that for now. We'll take the derivative of this, and I'll show you how that works. And this is plus c1 and c2, but let's just make it a plus c. We'll just say c equals c1 plus c2. They're all constants. None of it matters. So there you have it. That's the antiderivative of the integral. And let's check that that works. So f prime of x, take the derivative of 5x, or x to the 5th. That equals 5x to the 4th. We'll take the derivative of 4 over 6, x to the 6th. Well, that is plus 4x to the 5th. And the derivative of c is 0 for any constant. So that's a check, and we've now determined that that will work as far as our antiderivative is concerned. All right, so let's do this other one. I'll bring it down. And that was number 475. All right, so we'll do the same thing. Our capital F of x is equal to the integral of this whole thing. And we're looking for the integral of this, which is going to equal our first term x. That's x to the first. So that's going to be x to the 1 plus 1 over 1 plus 1. And this next one, x is x squared. So 2x, 2 plus 1 over 2 plus 1. And then just a plus c. Again, I illustrated with the c1 and c2 up there. But here we can do it all as one thing. So our integral is equal to x squared over 2. This is 2/3. 2/3 x cubed plus c. And again, let's check. And this is a good way to do it. You know how to take the derivative of this. So let's check. So the derivative of x squared over 2 is just x, because the 2 comes down, cancels with the denominator 2. And the 3 comes down, cancels with the denominator 3. And we have 2, 2, not 3. 2x squared. And the derivative of c is 0. So our check works.